In this video, we're going to look at what's called R or S configuration. RS configuration. And be really careful once we go through R and S to not get it mixed up with D and L. So remember, if I have a pair of enantiomers, right, if I have two molecules that are stereoisomers of each other and they're non-superimposable mirror images, one is going to bend light to the left, the other will bend light to the right, right? We had our L enantiomer, we have our D enantiomer. We're also going to give them designations with R and S as letters, and there is no correlation at all between RS and DL. So if something's R, it could be D or it could be L. We don't know. The only way to determine D and L is to go into lab and actually measure it. R and S, we're going to figure that out by assigning priority to groups and look at the order that that priority is ordered in around my chiral center. So just be really careful not to get those mixed up. There is no correlation which I can't spell, between RS and DL. Right? This is the direction it rotates or bends plane polarized light. Right? We need to measure this in lab. R and S, I had said it, and I will write this down here in a minute, but what we're going to do is we're going to look at the four groups that are bonded to my chiral center. We're going to assign them priority, and then we're going to look to see how that priority, how those groups are ordered around my chiral center. So it's something that we can do on paper. D and L we cannot. And you can have a molecule that's D that's R, you can have a molecule that's D that's S. There's no relationship between the two. The only thing we could say about them that would make them similar is that enantiomers are going to have opposite. If one enantiomer is R, the other enantiomer is going to be S. If one enantiomer is D, the other is going to be L. We just don't know if that D1 is RS. There's no, again, correlation between the two. So be really careful to keep those straight. So with R and S configuration, what we're going to do is we're going to look at the orientation of groups about the chiral center. Remember, our chiral center is a tetrahedral carbon, so an sp3 hybridized carbon with 4 different groups assigned to it. Our S configuration has nothing to do with the direction that it bends light. That's D and L. So what we're going to do is we're going to assign priority, and we're going to have a list of rules for doing that. And then we're going to look at the orientation. So our list of priority rules. Our first one, it says that the higher the atomic number, the higher the priority. So if my chiral center was bonded directly to, let's say, a hydrogen, a carbon, a bromine, and then we'll put a hydroxyl group on there. So what I'm comparing in this case, I'm looking directly to see what it's bonded to. So I'm comparing a hydrogen to a carbon to a bromine to an oxygen. And bromine has the higher atomic number, right? And we would just get this off the periodic table. Oxygen is going to be my second one. Carbon is going to be third, and then hydrogen, it has an atomic number of 1, right? It's always going to be my lowest priority group. So the higher the atomic number, the higher the priority. I'm making the highest priority number 1. Right, it's number 1. My second rule, if that atom that the chiral center is bonded directly to is the same, then we're going to go out and look at the next atom. If that's the same, then you look at the next atom. So just keep going out until you see a difference. So if bonded directly to the same atom or same type of atom, if it was same atom, we'd have a double bond. And then it wouldn't be a chiral center. We're going to look at the next atom. Etc. So just keep going out till you see a difference. So if I had carbon, I'm going to put a CH3 group here. Here, let's put a CH2, CH3. A hydrogen, and another hydroxyl group. So priority, we're going to use both of our rules. You do these in order. So first one, higher atomic number, higher priority. So I'm comparing carbon, right? I'm looking at the first thing it's bonded to carbon, to oxygen, to hydrogen. And I know oxygen has the higher atomic number, so it's my highest priority, right? It's number 1. And then carbon would come next, but this is where I need my second rule. I have 2 that are bonded to carbon. So then I'm going to go out and I'm going to look to see what they're bonded to. So I'm just going to kind of redraw. This is going to be my carbon on the top, my methyl group. That carbon is bonded to 3 hydrogen. And then if I look at this carbon, that carbon is actually bonded to another carbon and 2 hydrogen. And then that carbon is bonded to 3 hydrogen. But we actually get a difference at this point. So I kind of think about like what trumps what. So if I'm comparing these guys, these 2 carbons are the same, so I can ignore them. So then I'm going to go out to the next difference. I have 2 hydrogens, so that hydrogen and then let's say that hydrogen cancel. And then the thing that's left different is a hydrogen and a carbon. That carbon is higher in priority, right? Rule number 1, higher atomic number, higher priority. So this is going to be higher priority than this, right? Carbon bonded to 1 carbon and 2 hydrogen is going to be higher in priority than a carbon bonded to 3 hydrogen. This looks a little weird because I don't have these guys on here, but I just drew the same molecule. And then my lowest priority group is always going to be my hydrogen. If you have a hydrogen, it's always going to be your lowest priority group. Rule number 3, if you have different isotopes of the same atom, so they're going to have the same atomic number, the one that has the higher mass number is going to be higher in priority. So the higher the mass number, the higher the priority. So remember, isotopes are atoms of the same element. So if I was comparing hydrogen to hydrogen, right, they both have to have 1 proton in the nucleus, otherwise it wouldn't be hydrogen, right? The number of protons is what defines an atom as belonging to a particular element. But I can change the number of neutrons if I want. So hydrogen with a mass number of 1 would have 1 proton and 0 neutrons. Hydrogen with a mass number of 2 would have 1 proton and 1 neutron. And then the relationship between those 2 are isotopes. That number that I drew is the mass number. So if I'm looking at these 2, this is going to be higher in priority because it has the higher mass number. If I was comparing carbon-12 to carbon-13 is going to have the higher priority. Hydrogen-2, and this is how you're going to see it, it's actually called deuterium. It actually gets its own name. Hydrogen-2 also works, but the way that you're going to see it, the way your book and I am going to draw it in lab and pretty much every other organic instructor, is we're going to use a D. So if you see a capital D, it is hydrogen, but it's hydrogen with a mass number of 2. So an example if I take carbon, I bond it to a hydrogen, I'll bond it to a deuterium. Let's do a ethyl group and a propyl group. And we're going to assign priority. So again, the first thing you want to look at is what it's directly bonded to. So I have a hydrogen, a deuterium, a carbon, and another carbon. The atomic number of carbon is higher than that of hydrogen. Deuterium and hydrogen have the same atomic number, right? They're both 1. If I wanted to stick them up here, they'd both get a 1. So the 2 carbons are my options for 1 and 2 for highest priority. And then since they're both bonded to carbon, we look to see what they're bonded to. So this carbon here is bonded to 2 hydrogen and a carbon. This carbon is bonded to 2 hydrogen and a carbon. So now I have to keep going. This carbon, right, the one I'm making my little arrow thicker, is bonded to 2 hydrogen and another carbon. This carbon is bonded to 3 hydrogen. So 2 hydrogen and a carbon is higher in priority than 3 hydrogen. So this is number 1, this is number 2. And now I have hydrogen and deuterium, they have the same atomic number, so we're going to use rule number 3. The higher the mass number, the higher in priority. So deuterium gets number 3. Hydrogen really is always going to be last. So that is my lowest priority group. One more rule. And that says that if we have a multiple bond, we're actually going to treat it as being bonded to that number of atoms. So if I have a double bond between carbon and another carbon, I'm going to think of that first carbon as being bonded to 2 carbon. It is only bonded to 1 carbon, but that's how we're going to treat multiple bonds. So treat multiple bonds as being bonded to that number. So a double bond, think of it as being bonded to 2. A triple bond, think of it as being bonded to 3 of atoms. So kind of as an example, if I have a double bond, and then this is where my chiral center is. So I'm just going to kind of draw a little slash through it. That's where it's attached. And then it's bonded. The way that I kind of want to think about this is I want to think that this carbon, right, the one that's attached to my chiral center, this carbon is bonded to a hydrogen and 2 carbon is how I want to think about that. If I had a carbonyl, remember a carbonyl is a double bond to an oxygen. So let's say I have an aldehyde functional group. And again, this is where I'm attaching it to my chiral center. So I'm looking at this carbon, and I'm going to think of that carbon as being bonded to 2 oxygen and a hydrogen. So we're going to think of, right, the atom that has that multiple bond is being bonded to that number of those atoms. If I was to look at a triple bond, again, this is where it's attached to my chiral center. So this is where it's attached. So this carbon, I'm going to think of it as being bonded to 3 other carbon. It actually then gets bonded back to itself. It's kind of confusing, but usually this is enough to be able to do it. So a couple more examples before we actually start doing the R and S. So I'm just gonna, they're not always drawn in this kind of format that I've been doing, right? I've just been doing kind of a traditional tetrahedral. Usually we see them in skeletal structures, but they're still tetrahedral, right? If I was to put 2 groups on here, one of them is coming out at us, right? If you were to build a model of this, and then one is going back. So I'm going to put an OH group and a hydrogen. We're going to do a couple. I just want to draw some things in different conformations so you can get used to seeing how they might be shown. I messed that one up a little bit. Sorry, guys. I want to get a triple bond in there, but I need to show you some stereochemistry. Oh, I'm changing what I want to do. I'm going to do a cyanide group. Let's put a hydrogen here. I'll come back and I'll explain the cyanide group. If you guys don't remember what a cyanide group looks like, it's important. You'll see CN, but it's important to know how they're connected. So let's put a carbon. Let's do an H2. So I have an amine functional group also. And let's just do these two to start. So my chiral center, right, that's this one. My carbon bonded to 4 different groups. And my options, right, we're going to assign priority, is I have hydroxyl group, right? So I have an oxygen, I have a hydrogen, I have a carbon, and another carbon. So of those, my hydroxyl group is going to be 1, right? Oxygen has a higher atomic number than carbon and hydrogen. And then hydrogen's always going to be last, that's going to be 4. So now it's between the 2 carbons. This carbon is bonded to 3 hydrogen. This carbon is bonded to 2 hydrogen and another carbon, which means it's going to be higher in priority. This is my chiral center. So I have a hydrogen, I have a carbon, I have another carbon, and I have another carbon. So hydrogen's going to be lowest, so we need to start looking at these carbons. So this carbon here is bonded to another carbon and 2 hydrogen. Oops, I didn't mean to get rid of the green there. Oh well, it's got to go eventually. This carbon is bonded to a nitrogen and 2 hydrogen. So nitrogen has a higher atomic number than carbon does, right? This one's bonded to 2 hydrogen, a carbon. This one's bonded to 2 hydrogen, right? There's 2 hydrogen on that carbon and a nitrogen. So I know that the nitrogen is going to take priority over that carbon. So if we're kind of working backwards, we know that this is going to be my lowest priority. And then this one is going to be number 3. The reason I know that I'm putting that to number 3 is that this carbon is also bonded to a nitrogen. So this is where the fact that you have to know what the structure of cyanide looks like. There's actually a triple bond between the carbon and the nitrogen in cyanide. And then there's a lone pair on that nitrogen, but there's a triple bond there. So when I'm comparing this carbon right here to this carbon right here, this carbon is bonded to 2 hydrogen and 1 nitrogen. This carbon is bonded to 3 nitrogen, right? If I have a multiple bond, I'm going to think of it as being bonded to that number of the atom. So I have a triple bond, so it's bonded to 3 nitrogen is how I want to think about it. So that one is actually going to be my highest priority group. And this one is going to be number 2. So now that we know how to assign priority, this is where we're going to look at their orientation. So what we're going to do is we're going to make sure that our lowest priority group is tilted back. If it's not tilted back, then we need to somehow rotate or tilt our molecule to make it that way. So with the lowest priority group going back, and again, that's important. So with the lowest priority group going back, what we're going to do is we're going to go from 1 to 2 to 3. So from highest priority to second to 3. So I'm actually going to draw like a circle, a little arrow going from 1 to 2 to 3 with my lowest priority group pointing back. If you go from 1 to 2 to 3 in the clockwise direction, it's going to be R. Again, now remember, this has nothing to do with the rotation of light. Just because it's R doesn't mean it's going to rotate light to, in the clockwise direction. It has nothing to do with that. It only has to do with the order of the priority, right? the orientation, sorry, of the higher priority groups on my chiral center, right? Nothing to do with bending light. So with your lowest priority group, go from 1 to 2 to 3. If that's in the counterclockwise direction, it's going to be S. So with your lowest priority group back, we're going to go from 1 to 2 to 3. If it's clockwise, R. If it's counterclockwise, S. Since we have priority assigned to these ones already, let's do our configuration. So in both of these, I actually have my lower priority group going back already, right? On this one, right, my hydrogen is dashed, which means it's going back. So I'm just going to look at where my my groups are. Oops. Sorry, I didn't catch that before, guys. If I was confusing you, I apologize. This should be number 2. I can't have 2 number 4s. It wouldn't be chiral if I had 2, right? Of the same. Okay, so the real number 4, hydrogen, is already going back. And I'm just literally then, 1 is here, 2 is here, and 3 is here. So I'm going to start with 1, and then I'm going to go to 2, and then I'm going to go to 3. So the direction that I'm drawing this arrow when I do that is counterclockwise. So that's going to make this S. If we do this one next, again, my lowest priority group is already going back, so I don't have to worry about it. 1 is here, 2 is here, and 3 is here. So as I go from 1 to 2 to 3, right, that's the direction I'm going. I'm also going counterclockwise, so this one is also S, right? As I connected those, let's do that again. Let's grab a different color, right? 1, 2, 3. So 1 is here, 2 is here, 3 is here. And the way that I'm dragging that, I'm going counterclockwise. So that would have the S configuration. Again, we have no idea which way it's going to bend light. We'd have to go in lab to measure that, right? No correlation between R and S and D and L. Let's look at some of these since we have them labeled already. So this one, right? My lowest priority group is not going back, right? It is going up. So what I need to do is I need to tilt it so that group is going back. And some folks are really good at visualizing in 3 dimensions. So the other way you can do it is if you can visualize yourself laying underneath this thing and looking up, right? So you're laying under here. Get that little 2 out of the way. We'll have to put it back. But you're laying under here. This is me with my hair. And you're looking up in this direction. Because if you're laying underneath it and you're looking up, then this group is going back. And if you can visualize it like that, then like more power to you. I'm super impressed and I wish I could. And some people can. So if you can do that, you don't have to redraw it. I'm going to redraw it. So what I need to do to make that group, right, my lowest priority group back, is I'm going to tilt the entire thing. So what's going to happen is I'm going to end up with kind of what looks like almost a Newman projection. So this carbon in the center is my chiral center. And I'm tilting it so my hydrogen is like back here. I'm not seeing it. So I don't have to even show it because I'm going to go from 1 to 2 to 3 and I'm going to know my hydrogen's back. So when I flip it that way, what I'm doing is I'm taking kind of this bottom part and I'm flipping it up. So this group, and we can look at a model, it might be easier. This group right here is going to end up here. And then my deuterium is right here, and then this is my propyl group. So we just kind of took the whole thing and tilted it back. So when I look at my priority, right, they haven't changed. Deuterium is still number 3. My ethyl group is number 2. And my propyl group is number 1. And then when I do the 1 to 2 to 3 thing, 1 is here, 2 is here, 3 is here. So I'm going to go in this direction. And again, it's counterclockwise. They're not all S, I promise. These just happen to come out S. So let's look at a model of that, how I'm tilting it back. Okay, so I built the motto. Having an ethyl and a propyl group on here is kind of big and awkward to look at, but it's getting it kind of in the same orientation. So my deuterium, I'm just going to use green. I have hydrogen going up, and then I'm going to hold it by that hydrogen. Here I have that ethyl group, so there's 2 carbons there. They're coming forward at you, and then the propyl group back here is going back. So what we're doing is we're actually going to tilt it this direction, right? I need to take this hydrogen, which is my lowest priority group, and I need to get it going back. So I'm going to take it and I'm going to tilt it this way. So let me get it all lined up right again because I switched it on you. So I have it this way, and then I'm going to tilt it. So when I do that, my ethyl group is on top, like in our drawing, right? I'm holding on to that deuterium, and then my propyl group is there. So my highest priority groups, number 1, number 2, and then number 3. So again, we just kind of tilted it back in that direction. We have one more example up here. And this one, I'm going to actually take a shortcut on you. So my highest priority group is actually coming forward. So for this one, you would have to tilt it, I would have to rotate the molecule and then tilt it, because we need to get that lowest priority group going back. We can't like pull off atoms and move it because now I just drew its enantiomer, right? We want to figure out the configuration of this one. So no breaking bonds. You can't do that. You can rotate them, you can twist them, you can visualize yourself laying underneath it and looking up. For this one, if you wanted, you could visualize, because the hydrogen is actually coming forward and we need it to going back. If you can visualize yourself jumping behind the screen and looking at it from the opposite direction, hydrogen would be going back instead of forward. Again, if you can do that, great. What I'm going to do is I'm going to cheat. And it's not even really cheating. I think everyone does this that has organic and does this sort of RS configuration. And this only works in this instance if your lowest priority group is coming out instead of going back. And I couldn't use this cheat with this example because it wasn't coming out. It was in the plane, right? It's up. If it's in the plane, it doesn't work. So if your lowest priority group is coming out at us, which this is, that's the complete opposite of going back. So what I'm going to do is I'm just going to go from 1 to 2 to 3. I'm going to see if it's R or S, and then I'm going to change my answer. I'm just going to reverse it, right? Because this is actually the complete opposite of what it needs to be. So I'm going to take the complete opposite of my answer. And again, this only works when your lowest priority group is coming out at you. If it's in the plane, you can't do it. And I'll write that in a minute after we do the actual configuration. So I'm just going to leave it where it is. I'm not going to rotate anything. I'm going to look at where 1 is, I'm going to look at where 2 is, and I'm going to look at where 3 is, and I'm going to go from 1 to 2, to 3. Oop, I hovered there too long. So I'm going to go from 1, I'm going to get it from 1 to 2 to 3. And when I go in that direction, it is R, right? Because I'm going clockwise this time. But I know that my answer is completely backwards because I did this with hydrogen coming out instead of going back. So once again, my answer is S. I am just going to take the complete opposite of what I should because my lowest priority group is the complete opposite of what it should be. So kind of back to our directions here. Lowest priority group back, right? We're going to go from 1 to 2 to 3. That's clockwise R, counterclockwise S. We can add to this if the lowest priority group is going forward or coming forward. I'm not sure what the proper way to say that is. Reverse your answer. If the lowest priority group is in the plane, then you're going to have to manipulate the molecule some way. If it's easier to manipulate it so the lowest priority group is going forward, just do that and then take the reverse again. So if your lowest priority group is going back, go from 1 to 2 to 3, clockwise is R, counterclockwise is S. If the lowest priority group is going forward, still go from 1 to 2 to 3, but if you get R, change it to S. If you get S, change it to R. You could actually say if the lowest priority group is going forward, go from 1 to 2 to 3, counterclockwise R, clockwise S. That's actually kind of not the right way to think about it, because clockwise is always R. It's just that we're doing it backwards, so you need to reverse your answer. So let's do this as our example. So NH2. So I'm showing that group coming forward. I do have a hydrogen on there. I'm not showing it because I'm using skeletal structures, but I do have a hydrogen. And then because that amine group is going back, that means that hydrogen is coming forward. So my lowest priority group, which is going to be hydrogen in this case, and it doesn't always have to be hydrogen. If you have hydrogen, it'll be your lowest priority group. If you don't have a hydrogen, then it won't be hydrogen. It'll be something else. So in this case, it is hydrogen. I'm just going to redraw it so it's not squished so far in there. But that group is coming forward at us. I know the bond isn't really shorter than the other, but the hydrogen was getting messy. So we're going to assign priority. I'm comparing a nitrogen to a carbon to a carbon to a hydrogen. Nitrogen has the higher atomic number, so that's going to be number 1. This carbon is bonded to 1 carbon and 2 hydrogen. This carbon is bonded to 1 carbon and 2 hydrogen. So then we have to go to the next one. This carbon is bonded to 3 hydrogen. This carbon is bonded to 2 hydrogen and another carbon, so that carbon wins, right? It trumps, the carbon trumps the hydrogen. So this direction is going to be 2. This direction is going to be 3. Hydrogen is my lowest priority group. Usually I won't number it just because there's just a lot of stuff there. It's easier to see for me if it's cleaner. So I'm just going to leave the 4 off. I know that it's 4. And then my lowest priority group is coming forward. So what I'm going to do is I'm going to do the clockwise counterclockwise thing, and then I'm just going to change my answer. So I'm going to go from number 1 to number 2 to number 3. Right? In the order that I'm doing that in this direction. It's kind of funny, I come up with the same answer every time. It's not always that, I swear. So I'm going from 1 to 2 to 3. I get R, right? That's clockwise. But my lowest priority group is coming forward, so I need to switch that to S again. I'm just coming up with these randomly, and apparently I'm on an S kick today. Let's do... hydroxyl group, and then just a methyl group. We're doing skeletal structures, so we can just leave it. So this one, assigning priority of oxygen. I have a carbon right here, I have a carbon right here, and I have a carbon right here. So oxygen is going to be my highest priority group, right? The one with the higher atomic number, so the atomic number of oxygen is higher than that of carbon. And then of these carbons, this carbon is bonded to 3 hydrogen. This carbon's bonded to 2 hydrogen and a carbon. This carbon is bonded to 1 hydrogen and 2 carbons. So that one's going to take priority. Next, so this is going to be number 2, going up in this direction. This one is going to be number 3, and then my lowest priority group in this case is my methyl group. So not hydrogen, but it's still lowest. And I'm just going to leave the 4 off again for clarity, because I'm going to go from 1 to 2 to 3. I just need to make sure that that group is back, and it is. So going from group 1 to group 2 to group 3, I know my clocks. I am actually R this time. I just got an S habit. So this time I'm going clockwise. So this would have the R configuration. So enantiomers, remember we said our enantiomers were our non-superimposable mirror images. Right? They're mirror images of each other, but we can't superimpose them, making them oriented differently in 3-dimensional space, making them stereoisomers. We said they're optically active, meaning that they can rotate light, right? They're chiral. And they have the same physical properties, but they're going to rotate light in opposite directions. They will also have opposite configuration. So if one enantiomer is R, the other enantiomer will be S. So enantiomers will have opposite configuration at all chiral centers. They can have more than one. If they do, all the chiral centers between the two enantiomers will be opposite. We're going to have other types of stereoisomers in this chapter, and I will give you sets of them, and one way to tell if they're enantiomers or one of the other types is to assign configuration. So if I have one molecule and it has two chiral centers, and the first one is R and the second one is S, when I look at its pair, if it's an enantiomer, then the first one will be S and the second one will be R. If I have a pair of enantiomers and one of the molecules, right, one of the stereoisomers is R on the first one and R on the second, then the other one will be S and S. So if you're comparing one enantiomer to, right, one molecule to its enantiomer, it will have opposite configuration at all chiral centers. This isn't going to be true of our other types of stereoisomers, so it's going to be one way to be able to differentiate between them. So we'll have opposite configuration at all chiral centers. Remember, these guys are chiral, so they have no plane of symmetry. This is also important to note because I will have a type of molecule, they're not actually stereoisomers, that have chiral centers. They have opposite configuration at all of them, but they have a plane of symmetry, making them achiral. So don't forget this part also. So if I was to draw, and I'm just drawing these randomly, we're going to have to figure out if they're enantiomers or not by assigning configuration. So I'm going to put a bromine and a hydrogen. And then I'm going to put the hydrogen here and the bromine and then my methyl group. So our question, are these enantiomers? And again, if you're really good at seeing things that I'm drawing in 2 dimensions in 3 dimensions, and you can rotate those in your mind and see if they're non-superimposable mirror images, then great. I can't do that. So what I'm going to do is I'm going to assign configuration to the chiral centers. I only have one chiral center. So if the configuration is the same, then they're not enantiomers, because enantiomers are going to have opposite configuration at all their chiral centers. If one is R and the other is S, then they are enantiomers because I have opposite configuration at all chiral centers. Remember, if I have one chiral center, it's going to be chiral, so I don't have to worry about this whole plane of symmetry thing. I do have a chiral center, right? This carbon is chiral. I have a hydrogen, a methyl group, a bromine, and a propyl group attached to it. So we're going to assign configuration, or assign priority, figure out its configuration. If it's the same for both of these, not enantiomers. If it's opposite, then they are enantiomers. So my highest priority group is going to be that bromine, right? It has the highest atomic number. And then I have my methyl group and my propyl group. The methyl group, the carbon's bonded to 3 hydrogen. The propyl group, the carbon's bonded to 2 hydrogen and a carbon. So that's going to be number 2 and then number 3. And then hydrogen is number 4. I have that hydrogen group going back already, so I can just do the 1 to 2 to 3 thing. So 1 is here, 2 is here, 3 is here. So when I go from 1 to 2 to 3, I'm going in the clockwise direction. My lowest priority group is going back, so I can just leave it. I don't have to do anything with it. My second one, this one's a little trickier. So my lowest priority group is actually in the plane. It's actually not coming out at us. It's not going back. It's actually in the plane. So this one, I'm going to have to manipulate it. And if you can do it in your head, that's fine. So like this one, what you would have to do is kind of like jump into the screen and look down this direction, right? I want to view it from here is kind of how I want to see it. Because if I view it from that direction, right, if you kind of jump into the screen and view from that direction, the hydrogen's going back. If you have a hard time doing that, then I'm going to do the kind of draw almost a Newman-y sort of looking thing. It's not, because I'm not drawing both carbons, I'm just drawing the front. But when I do that, I'm going to end up with, and again, I remember I'm just looking down this direction. My bromine is going to be over here. This is going to be that methyl group, and then this is going to be my propyl group. So highest priority is still my bromine. It's the same order. And then when I go from 1 to 2 to 3, this time I'm going counterclockwise, so this is S. So because one is R and the other is S, the answer is yes, they are enantiomers. You could manipulate those where they are mirror images and they are not superimposable. If I would have gotten R for both of them, no, they're not enantiomers. If I would have gotten S for both of them, no, they're not enantiomers. But because it's opposite, and I only have that one chiral center, right? So it's opposite at all chiral centers, yes, they are enantiomers.